Okay, I'm going to get started in just a moment. Just getting my paper set up and whatnot. Hey, there's Kyle. You did make it up right on time. About to get started right now. So tomorrow, Friday the 22nd, is the AP test for statistics. And today's the last day of any type of review people can take or whatever. I'm going to be doing the same thing I did the last couple of days, and we'll see how this pans out. So, of course, as I said in the chat, if you have any requests, please put your request in the chat, and I'll find a problem that fits your request, and we'll go from there. So, let's see if there are various problems that I do want to do and don't want to do. We'll see how that kind of plays out. I don't want to do that one. Let's start with something like this. Start with something very basic, simple. Zoom in on that. And then we'll see what other problems can kind of come our way. There we go. Here's the problem we got. Consider the following dot plot. Calculate and compare the mean and median. Now, obviously, this is not going to be the basic kind of problem you're going to be seeing on tomorrow's AP test. But it's just a good reminder. It's just a good reminder as to what you have in front of you. They're asking for you to calculate and compare the mean and median. And then B, comment on whether your answer was as expected. Part B has to do with the shape of the graph. Just as a quick side note in terms of describing a distribution like this, the acronym, which every teacher has their own acronym, the acronym that I have, or that I've been using in regards to describing a distribution like this, has been CUSS. C-U-S-S. Center, unusual features, shape, and spread. Now, in terms of the shape of this particular graph, it is skewed to the left. And because it is skewed to the left, the mean has most likely been pulled to the left or pulled towards the lower numbers. That's the expectation based on the shape of that graph. And that's something that you could comment on in part B, which we'll get to in a moment. But for right now, they want you to calculate and compare the mean and median. Just at a quick glance, 10, 14, 17, 19, looks like 21 data points. And if there are 21 data points, 10 on the left, 10 on the right, and then the one right in the middle would be the median. So, well, got 10 and 10, which means the median has to be at 5. The median has to be at 5. A quick way of going about the mean, obviously you could just add them all up and divide by 21, but if you didn't feel like doing that, you could just type in, oh, there we go, the data points based on what you see, and I'll show you how I did this in a moment. There we go. 21 data points. Pretty self-explanatory based on the fact that there's 1 for 1 and 1 for 2 and 2 for 3 and 3 for 4, etc. And you get the 5 6s and the 5 7s. That's what I put into the list. If you're able to type that in quickly, then obviously you can easily get an average right there, an X bar of 5.04. So then the question then becomes, okay, 5.05, I guess, if you want to round it for the mean. 5 should definitely be the median, based on it being the center data point. That's actually a comment on whether your answer was as expected, unless I typed something in wrong. No, the mean was not pulled down to the left. It seemingly should have been, based on the fact that it was skewed to the left. That's where the tail was. Yeah, let's see what the back of the card says. Ah, there we go. First of all, 5.05 being the X bar, the mean, and the median being 5. This was not what was expected. When data is skewed to the left, the mean is usually less than the median. That's exactly what we talked about. In terms of data being skewed, it tends to skew, or the mean tends to be pulled in the direction of the skewness. Paige, I believe your exam has 2 questions. Of all the information that I've been trying to forward to you guys in regards to the AP Stat test, I'm looking an email up right now. I believe that it should have 2 questions. See, now I'm going to have to search College Board. I had an email, but now I'm going to find a link that I'm going to put into the chat in a moment. Course description. That's the old one. Where's the 2020 one? Silliness. Yeah, it should be 2 questions. I'm just trying to find the 2020 AP statistics information. I found something on Khan Academy, but that's not gonna help me. Here we go. Well, no, now that's a sample question. I had all the information at one point. I've been forwarding it to you guys. Yeah, but anyway, I digress. Let's see what else we got. Obviously, over the past several weeks, I've been forwarding you guys in my class. I've been forwarding you information that I've been getting from College Board in terms of signing in and practice signing in and making sure that your computer fits all the requirements as to what they're asking for. You know, the benefit that you guys have as AP Statistics is the fact that since it is one of the last tests during the 2-week process, hopefully all of the bugs have been worked out. But that remains to be seen. Let's see what we're going to do next, though. I want to do another problem. And I don't like some of these problems. A lot of these problems that I'm looking at have to do with chi-squared, which obviously is not on your test, which I don't want to do as a result. There we go. There's a good one. Okay, let's bring this one into play. There we go. Boom. The professor of a large survey class is instructed to give final grades in the proportions 10% A's, 20% B's, 40% C's, 20% D's, 10% F. One semester she gives that in a class of 150. Is there statistical evidence that the professor is giving more A's than the instructions call for? Now, if this problem had talked about all the letter grades, and I want to double check the back of the card real quick. Yes, which it does for part B. And this is actually a good distinction. For part A, since they're only talking about A's, we can do a proportion test. But for part B is actually asking for what is known as a chi-squared test, something that we never got to, and chi-squared will not be on this year's AP Stat test. Part A is only asking about the A's. Part B is saying, is there statistical evidence that the professor is not giving a distribution of grades consistent with the instructions? So it's not just talking about one category, part B. Part B is talking about all the categories, A, B, C, D, and F, all 5 categories. So part B is what we would do for chi-squared, not on this. Let's just deal with part A. Is there statistical evidence that the professor is giving more A's than the instructions call for? Well, I'm going to write down some information above the card, and then I'm going to zoom out in a moment. They are expecting 10%, and not X bar, P hat is giving 22 A's out of 150. Okay, let me zoom back out for a second. Come on, little thing. Okay, you're not zooming out the way that I want you to. There we go, much better. Okay, So the expectation for A's was 10%. The sample information that they got here, the X and N, that number of successes and the number of trials, was 22 out of 150. For part A, when they're saying is there statistical evidence that the professor is giving more A's than the instructions called for, it seemingly is that we want to run a one prop z-test, which we will. We absolutely will. I'll show you the back of the card in a moment. But let's just see what happens. In terms of the test, I would say the null hypothesis would have to be, well, they're expecting 10% A. And the question, is he giving more A's? So the alternative would have to be greater than. Running through assumptions, conditions, you could go through the expectations, assumptions and conditions. I was thinking expectations in terms of expected successes and expected failures. Now, in terms of expected successes versus expected failures, clearly both are greater than 10. 150 is large enough sample. A class of 150. Now it says a professor of a large survey class is instructed to give final grades in the proportions of that. And then one semester, they give out that in a class of 150. It's reasonable to say 150 is less than 10% of all students at that university, I guess. But it's we're looking at the entire class of 150, so we do have to have a little wiggle room right there in terms of how we describe the 10%. I guess you could say randomness could be inferred based on randomness of students who take class, but more importantly, independence of grades feasible, meaning you getting an A doesn't affect another person getting an A, or vice versa, or whatever grade you end up wanting to get. But we want to run a one prop z-test. Obviously, if you have the calculator, fair game. If you don't have the calculator, there are other resources that you can use, as we've talked about. 10%, 22 out of 150, alternate being greater than. Calculate that thing out. We get a p-value of 0.028. Okay. 0.028, that's small enough. Definitely small enough. Meaning, because p-value is so low, 0.28 being less than 0.05 alpha, we reject the null. There is evidence to suggest. Now again, I go with the wording of the question here. Is there statistical evidence that the professor is giving more A's than the instructions called for? There's evidence to suggest, and I'm just going to literally copy it word for word. There's evidence to suggest the professor is giving more A's than is called for. My handwriting is atrocious today. You can't even see what I'm writing. Did I not zoom out far enough? Come on, you. There we go, much better. That was terrible for a second. My handwriting is atrocious today, and I apologize for that. You fool. There we go. Hey, it's Omar. Why is Null always getting rejected? He's a really nice guy. Oh my. I'm going to put a meme link in the description, or in the comments in a moment. Just for fun, as I can. Where are you? Copy image address and throw that in there. There you go. That's for you guys. You click on that. Let's see where we go next. Oh, right, I wanted to show you the back of that card real quick. Let me show you the back of that card real quick. Now, you can see for part A that they do end up getting the p-value that we got, the 0.028 p-value, which is exactly what we got. There's evidence that the professor is giving more than the instructions call for. But look at part B. Part B, that little symbol, this is a chi-squared goodness of fit test. That is something, again, we have not covered this year, and, well, mainly we didn't cover it because of COVID, and they are not testing you on it for the AP test this year. So you don't have to worry about Part B. Let's see where we're going to go next with this. Oh, there we go. Perfect. Okay, let me zoom in on this card. There we go. The runs scored per game during a 3-week period for each of 2 baseball teams is shown below. Team A, Team B. Now, before I even read any of the questions, just some comments about the shape of the distributions, because this may come in handy once we look at the questions. Team A looks like they have their peak somewhere around 3 and 4, and it looks more normal than Team B. More normal. I mean, more approximately normal, more nearly normal. One could argue that Team A is somewhat skewed to the left, but because of the way that the right side of the graph works out, I mean, that's a little bit of a hard argument. Whereas Team B, there's more evidence for Team B being skewed to the right. Yes, it does have its peak around 2, but it does have evidence that it's skewed to the right. Anyway, let's just see what the questions have to say. The standard deviation of runs scored for Team A is 1.5. Explain what this says about variability. Now, I've been trying to define standard deviation in words for you guys since the beginning of the school year. And the formula for standard deviation is where you take the deviations from the mean, you square them, you add them all up, you divide by n minus 1. It's not that standard deviation is exactly what I'm about to say, but standard deviation is similar to that of, on average, how much deviation does each data point have from the mean. So if you picked a random data point, on average, it would have this type of deviation. So for Team A, on average, they deviate about 1.5 runs from wherever the mean is, which again, the mean would probably be between 3 and 4, as a guess. So the back of the card actually does say. The back of the card, I'll just put it down. What am I even holding it up for? There we go. The standard deviation is representative value for how many runs off from the mean Team A scores in any given game. Most games, the team will score within 1.5 runs of the mean number of scores. Which again, that last statement's not necessarily needed, but there's that standard deviation. It's a representative value for how many runs off, meaning on average, how much do they differ from the mean. Let's look at part B. Part B, looking at the dot plots, what can be said about the difference between runs scored by the 2 teams? Explain. The difference. Well, I mean, one thing you could definitely say, on average, it seems that on average, Team A is definitely scoring more than Team B. We talked about where the peaks were. Yes, Team A's average seemingly is around 3 and 4, based on the visual of the dot plot. Team B does have its peak around 2, but because it seemingly is skewed to the right, we can say that that average has been pulled up a little bit, but I don't think it's been pulled up as much as Team A. I think it's fair to say that Team A definitely scores more in terms of the difference than Team B. Come on, card, do your flip. Team A, scoring 3 or 4 or 5 runs in many games, appears to score more runs in any given game than Team B, which typically scores around 2 runs per game. Yeah, perfect. Again, when you're describing a distribution, and that's something that I did before I even read the questions, I used that acronym CUS, describing the center, unusual features, the shape, and the spread. Very important. Part C, a 95% confidence interval estimate for the difference in mean runs scored per game is that. From this calculation, is there evidence of difference? Explained. Okay, first of all, let's go back to the confidence interval. Based on this calculation, we can definitively say we are 95% confident that the true difference in runs scored, the true mean difference in runs scored between Team A and Team B is in that interval. We're 95% confident we have it in that interval. Now, what that means, 95%, again, we've talked about this for many months. It basically means that if there were many intervals calculated based on many different samples that were taken, many different samples, 95% of those intervals would capture the true difference, and 5% would not. We are simply hoping that we are one of the 95%. From this calculation, is there evidence of a difference? Unfortunately, no. There is not. There's not enough evidence. Explain. 0 is in the interval. Because 0 is in that interval, there is a possibility. You can't say 95% chance, by the way. You can't say that. You can just say that since 0 is in the interval, there is a possibility that 0 is the true difference in means. It's possible. And because of that, unfortunately, that there's not enough evidence to show a difference. Not enough. See what the back of the card says. Since 0 is in the confidence interval, there's not sufficient evidence to say that the mean numbers of runs scored by the two teams are different. Yeah. Very important. I love questions like that. Now, obviously, some questions like the ones we just did, there are no calculations needed. A lot of the questions that they're going to be doing on tomorrow's AP Stat test, a lot of the questions are not going to involve calculations, per se. I mean, obviously, you should have a calculator ready, just in case, for some basic calculations. But a lot of the stuff that you're going to be doing is based on inference, is going to be based on description of the problem, wording of the question, you, as a student, constructing a proper conclusion based on whatever numbers they give you. So, we'll see how that goes. Fluffy language. Do not say anything definitive. Do not say that something is, say that it appears. Don't say, well, clearly this null hypothesis is wrong. No, there's evidence to suggest that it's wrong. Always use that fluffy language. Always, 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 always. Let's look at this question. Suppose the number of minutes per day high school students spend text messaging is normally distributed with a mean of 21 minutes. That's actually something I wanted to point out, though. Assumptions, conditions. They're probably going to, not harp on, but they're probably going to drill you guys on assumptions, conditions as well. So something to look out for. Assumptions, conditions to show that something can be normally distributed, but for questions that do tell you, hey, it's normally distributed, good. I don't have to do assumptions, conditions. I can just move on. Anyway, Kyle, the answer's not 7. Shut up, Kyle. Anyway, back to this. Which is more likely? A simple random sample of 25 students text messaging an average of less than 20 minutes per day, or a simple random sample of 100 students text messaging an average less than 20 minutes per day. Explain. Now, this is one of the keys of statistics, and it relates to the law of large numbers, where you can have a theoretical probability and an experimental probability. And the more trials that go into the experimental probability, the closer it gets to the theoretical. How that relates to this problem. They're saying that the mean is actually 21. Assume that that's true. They say suppose that that's true. The mean is 21. You have a sample size of 25. Maybe they get an average less than 20 minutes. I don't know. But it is more likely that you would get an average less than 20 minutes per day with a smaller sample size. And the reason for that, and I can actually write it just right here. I'll write it just right here. The reason for that is because of sigma over the square root of n. This has to do with sampling distributions. Let me write that up here. Sampling distributions. When you have a certain sample size, let's say like 25 students, and you average their, what did they say, the number of minutes spent text messaging per day? Yeah. You can see that the sample size goes on the bottom of that fraction. The larger the sample size, the smaller the sampling distribution's standard deviation. The larger the sample size, the smaller the variability. Remember, standard deviation is a measure of spread. It shows you how much the data varies on average. If you have a larger sample, like 100, you're going to be dividing it by a larger number compared to 25. And we can see on the back of the card here, the standard deviation, there it is. The standard deviation of the sampling distribution is proportional to 1 over square root of n, which is smaller for larger n. Thus, the probability of a sample mean more than 1 minute less than the population mean decreases for larger n. So if the sample size is 25, is more likely to have a mean more than 1. Again, that wording, I'm not a fan of the wording on this card at all. I'm really, really not. The wording on this card is terrible. I much prefer what I just showed right here. If you're giving an explanation as to why you're more likely to have a mean under 20 minutes for a smaller sample size, this is perfect rationale for it right here. Let's look at part B. Part B. Suppose the sampling distribution of x bar for sample sizes of 100 has a standard deviation of 0.8. Okay. What is the probability a simple random sample of 100 students text messaging an average of more than 23 minutes? See, now they're not saying, for part A, it was which one is more likely, but they're not actually asking you to calculate anything. For part B, they want you to calculate it. Let's see what we're going to do with this. I'm going to zoom out just a little bit. Come on, you. There we go. Good enough. Okay. So in terms of this calculation, they're assuming a mu of 21. Now, the way that they worded this, and let me bring this thing back here real quick. Suppose the sampling distribution of x bar for samples of size 100 has a standard deviation of 0.8. It's like they've already done the calculation for us. They have already basically done mu over the square root of 100 is equal to 0.8. You don't have to change anything. You don't have to divide the 0.8 by anything. They're saying that already is the standard deviation of the sampling distribution. And they want to know the probability of getting more than 23 minutes. Oh, normal CDF, 23, comma, big number, comma, 21, comma, 0.8. That calculation should knock that thing out. Let's see what we get. Normal CDF, 23, comma, big number, comma, 21, comma, 0.8 to pow. Nice. Approximately 0.0062. Which is what the back of the card actually says. Good for us. The back of the card calculates it in a slightly different fashion. Here's what the back of the card actually says. You can see for part B, we calculate the z-score and then the probability that the z-score is greater than 2.5. This is also sufficient. I mean, I prefer doing it like this, but it could be done either way. That's part B. Part C. I'll just hold the card up. Suppose the original population is not normal, but rather is skewed right to the higher values. How would your calculation in part B change? Suppose the original population's not normal, but rather it's skewed right. Meaning skewed right. Oh, you can't see that. Moving up. There we go. Skewed to the right. Meaning that there are a whole bunch of people who maybe the mean is right here. I'm just guessing the mean is 21 minutes right here. And most people are in that range, in that bubble. But then there's like a few people who like text message maybe like several hours throughout the day or some junk like that. I don't know. I'm just speculating based on what they said. How would your calculation in part B change? It would not change at all. It would not change at all. I would not change a thing. And that has to do with what we learned in that chapter of sampling distributions. It doesn't matter what the original population distribution looks like. Because what we are doing is we are working with sample means. And since you're working with sample means, you can either call it this, which I'll talk about in a moment, or you could talk it this. You can either refer to the fundamental theorem of statistics, or you can refer to the central limit theorem. They are both the same thing. They both reference the same thing. But basically, because of the fundamental theorem of statistics, as the sample size grows larger, the distribution of the sample means becomes more and more normal. It does not matter what the original distribution looks like. As the sample size grows larger, the distribution of the sample means will look more and more normal. And the back of the card refers to just the central limit theorem. The calculation would not change because central limit theorem, the sampling distribution of x bar, is approximately normal. Always. Fantastic. I love stuff like that. Let's see. Do I want to do this one? Maybe. Nah, we did a problem like that the other day. I didn't want to do that one. Oh, this is perfect. This is perfect. Okay. I'm zooming in. Zooming out a little bit. There we go. Perfect. 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 Excitement fills the air. Okay. A high school math department conducts a study to determine whether a new AP Stat textbook will lead to higher AP exam scores than the textbook that is currently in use. 2 AP Stat classes are scheduled. Each teacher has 18 students. And it is randomly decided which class will use which book, which is good. You always have to have randomization in these types of things. At the end of the academic year, the 18 students in each class will take the AP Statistics exam. Why is there a comma there? Whatever. And the department notes the scores. Okay. Identify the response variable, the treatments, and the experimental units. Now, response variable is whatever you're measuring in the end. Whatever you end up measuring in the end. Whatever result that you're going to be documenting. And that is going to be the scores on the AP Stat exam. Response variable. The treatments. The treatments are the manipulation in the experiment. The treatments are what you are introducing that's going to potentially affect the outcome of the response variable. In this case, the AP Statistics textbooks. Are they getting the new textbook or the old textbook? The experimental units. Now, the experimental units are basically the students at this point. They're the students. Oh no, my card fell. Goodness. Um, no, I say basically the students, but in reality, it's not so much. You see, because let me go back to the card real quick. They're going to note the scores, but think about what's going to happen. They're going to try and determine whether or not the new textbook was better than the old textbook. That's what they're really trying to determine. So what they're really going to do is they are going, sorry, Kyle, don't worry about that. What they're really going to do in this problem is they're going to average the class together. The class using the new textbook, they'll most likely average their scores together. The class that's using the old textbook, they'll average their scores together. It's a very minute distinction, but in reality, the experimental units are going to be the classes that are taking the course. Let me kind of show you on this card real quick. The response variable is the exam scores, the treatments are the two books, and the experimental units are the two classes, not the students themselves. That's a very minute distinction. I think that one could get away with saying that the experimental units were the students themselves, but the real way of putting it is actually the classes because they're averaging their scores together. Was randomization properly used? Well, keep in mind, the students taking the classes, they choose to take the classes. You can't force students to take an AP statistics class. In reality, that's unethical. But they randomized which class would get each textbook. And supposedly, I think it's reasonable to assume that each class is of equal ability level in terms of statistics. So I guess you could, if you really wanted to, you could randomize the students into the classes. But in lieu of that, in order to have that fit into their schedule, randomization of the books would be acceptable. Oh, there we go. Yes, the two books were randomly assigned to the two classes. Okay. Part C, was replication properly used? Now, you could think of replication in two ways. Now, replication is having multiple subjects go through the experiment. Replication could be this experiment being done again somewhere else. Like maybe we do this experiment at Barnegat High School and then they do that experiment at Southern. That would be also replication. Replication's dicey here. Again, I try not to read the back of the card. I didn't look at the back of the card for this one. It's kind of dicey here because they only ran through it in one school year with a class, and they took an average, I'm assuming, and then they run it through the old textbook with the class as well. No, there's no replication in the study. There you go. Each treatment was only applied to one experimental unit. If you consider the fact that each class is an experimental unit, as I said, it's kind of dicey here. It was not used properly. Teacher is confounding variable. Well, of course, teacher is confounding variable. Are there two different teachers? Two AP statistics class, each teacher. Yeah, so there's two different teachers. Teacher is confounding variable because different teachers have different ability levels. One teacher might be better than the other. Who knows? If you really wanted to run this experiment, you'd have to have the same teacher teaching both classes. Let's see what the back of the card says. If a difference in exam scores is noted between the two classes, it is not known if this is due to the difference in books or the difference in teachers. That is, the treatments are confounded with the teachers. Remember, a confounding variable is dealing with experiments, whereas a lurking variable, something that we talked about when we did correlation does not equal causation. A lurking variable would potentially be finding some kind of connection between two variables in a survey or an observational study. But a confounding variable is dealing mainly with experiments, where you run the experiment, but then unfortunately a difference may not be able to be known if, oh, was it the books or was it the teachers? We don't know. unless you eliminate that and have the same teacher teach the class. But they did say each teacher. And it's one of those things that they try to get you here. Each teacher. They'll really try to mess you up on that minute wording of the question. Ugh. Love it. I love it, I love it, I love it. Oh, here we go. Love it. Here we go. Another question where, again, there's not much in terms of calculations that you have to do. There's not much in terms of calculations that you have to do at all, but instead, it's writing, wording. I'm so glad that I spent the first 2 months of this school year doing nothing but writing. We wrote out conclusions. We wrote out assumptions and conditions. We wrote out so much stuff. We barely did any calculations until November. It just works out great for us. A pharmaceutical company plans to test a new, what in the world? Chemoprophylaxis. Okay, cool. That shows promise of reducing the proportion of people who come down with malaria in endemic regions. A random sample of volunteers will be inoculated, and after a suitable time period, their malaria infection rate will be compared to the known infection rate of the general population. Nice. Okay. Part A is asking about null and alternative hypothesis. Since we're talking about infection rate, is that a proportion, or is that something you can take an average of? Like, you could take an average if it's like 5 out of every 1,000 people, but if you're talking about a ratio, then obviously a ratio would be a proportion. Let me just know what we're talking about here. Oh, they don't actually say. Nice. Okay. They're just writing it out in words on the back of the card, which is oh so fun. You don't actually have to write out any formulas or anything like that. But to emphasize, a null hypothesis is when you assume nothing is happening, when you assume no difference, when you assume that nothing out of the ordinary has happened. A null hypothesis for this problem would be that the random sample, the new, I don't even know how to pronounce that thing, chemoprophylaxis, whatever, that the new drug, let's just call it, sure, let's call it a new drug. A null hypothesis would be that there's no difference between the new drug and the old drug. There's no difference in infection rate. Null hypothesis, nothing going on. Null hypothesis, no difference. Yeah. They're taking the original infection rate, and they're basically trying to say, well, maybe the infection rate's going to be different. Maybe the original infection rate's going to be, going to stay the same. Innocent until proven guilty. The alternate hypothesis is that there is a difference. They want to know if it's going to reduce it, reducing the proportion of people who come down with malaria. So the alternate hypothesis would have to be that the new drug reduces the people coming down with malaria. If I had to write that in, let me write that thing here. I'll write it out as a formula, just so you can kind of see it. This is also potentially doable. Null hypothesis would be that the proportion stays same. I'm not writing on the card. I am a little bit, so let's remove that. There we go. The null hypothesis is that the proportion stays the same, and the alternate hypothesis would be that the proportion reduces. If you, again, you don't have any concrete numbers for this, so you have to write it out in words. Null hypothesis, the infection rate stays the same, doesn't change. The alternate hypothesis, it is reduced. Now I'm also going to draw, I'll zoom out a little bit because I'm going to draw a little chart here. This is the type 1, type 2 error chart. Move that up a little bit, there we go. On top, I'm going to write the truth. The truth meaning the null is true or the null is false. That is the truth, but we don't always know what the truth is. And then our decision would either be to reject or fail to reject. If the null is true and you end up rejecting it, then you made a mistake. You made a type 1 error. If you're thinking about the skydiving example that I typically give with these things, a type 1 error would be saying, no thank you, parachute, I don't believe that you work, even though it actually does. You made a mistake, you don't get to go skydiving. If the null is actually false and you reject it, then hey, good job, you made the right decision. If the null is true and then you fail to reject it, hey, you made the right decision. If the null is false and you fail to reject it, you have made a mistake. That is a type 2 error. In the realm of our skydiving example that we've talked about in class, that would be the parachute in reality doesn't work. But you failed to reject it. So you made a mistake, and you did. Now, that comes into play with this problem. What is a type 1 error? You can see it right there at the top of the screen. What is a type 1 error in this context? What is the consequence of committing this error? Now, a type 1 error would be rejecting the null hypothesis. It would be rejecting the P not changing, and you conclude that the new drug reduces the malaria rate. Or you would basically say there's evidence to suggest. Can't see it. Why can't I zoom out? There we go. There's evidence to suggest that the new drug reduces the malaria rate. That's a type 1 error. Now, a direct consequence of that, you're basically spending money on a drug that doesn't do any better. Possibly, maybe it does worse. I don't know. But you're concluding that the new drug reduces the malaria rate when in reality, maybe it doesn't. You just spend money on stuff. Now, a type 2 error would be failing to reject the P. Failing to reject the P, not changing, I should say, or the null hypothesis. Basically, you are concluding there's evidence to suggest the new drug makes no difference, when in reality, it does. When in reality, the new drug does reduce the malaria rate. So a direct consequence would basically be, not only are you missing out on an opportunity to reduce the malaria rate, but you're also possibly costing people their lives because you didn't make that decision with the new malaria drug. Let's see what the back of the card says. Type 1 error, incorrectly rejecting the true null hypothesis in the context means that the new drug is not helping, but the company believes it is. They conclude that the new drug reduces the malaria rate when in reality it doesn't. The serious consequence would be that people might take this drug wrongly, thinking they will be safe from malaria. Yeah. Thinking they'll be safe, thinking it actually reduces the malaria rate, when in reality it doesn't. Type 2 error, incorrectly failing to reject the null hypothesis in this context means the new drug really is helping, but they don't realize it. The consequence would be that the people will choose not to take the drug that would really help protect them. Yeah, they want the generic route. I want a little bit more, what's the word? Morbid in terms of people dying. Because it's a big deal. It's a big deal. Yeah. That's a problem that they're not going to have on this test this year. Well, that's just fun. Yeah, we'll skip that one for now. I want to try and get something else here. Whoa. Nah, I don't want to do that one. Oh, here we go. Okay, let's talk about this. Zooming in. There we go. In the first two races at the dog track, the time in seconds of the dogs are given like this. Race 1, race 2. Now again, I'm not even going to read the questions yet. I'm just going to look at these two graphs and make certain inferences based on what these two graphs are actually saying. Race 1, compared to race 2, race 1 looks more normal. Although it does, if you ignored these 2 points, like the 68 and the 70, if you just ignored them, it looks a little bit skewed left, but because of them, it's almost like it completes the normality out of it. That's so weird. Whereas race 2 definitely looks skewed left. Definitely looks skewed left. Okay. In either race, are there any of the times considered to be outliers? Ooh. Interesting. Now, you have a couple options here. If you wanted to, real quick, if you wanted to, you could actually, because they gave you the numbers, they gave you enough numbers to be able to calculate this by hand. But if you wanted to, you could utilize the following formula. Now, if you had a calculator, I'll zoom out in a moment, but if you had a calculator, you could easily get the numbers for this. Oh, it fit. There we go. Basically, any data point that falls outside this range is considered to be an outlier. Any data point outside that range is considered to be an outlier. So, let's take a look. Let's reset that. Let's go here. There we go. So, race 1. 62, 63, 64, 64, 65, 65, 65, 66, 68, and 70. There we go. There's race 1. There's race 2. 61, 65, 67, 68, 69, 69, and 70. There's race 2. Okay. We run a 1var stat for L1. There we go. Looks like the interquartile range is 2. Interquartile range is 2. This is for race 1. And since the interquartile range is 2, I can do 64 minus 1.5 times 2. And then I can do 66 plus 1.5 times 2. There we go. For race 1, anything outside that range is considered to be an outlier. So for race 1, it looks like they have 70 seconds as an outlier. Easiest way of going about it, easiest kind of definition you could do is something like that. Let's do the other one. 1var stat, L2. Okay, it looks like the interquartile range is 4. 69 minus 65. So I could do 65 minus 1.5 times 4, and 69 plus 1.5 times 4. Anything outside that range is considered an outlier. Nothing is considered an outlier. Yeah, nothing is considered an outlier. It's crazy. See what the back of the card says. Back of the card, there are 11 values. The inspection given, blah, 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 Q1, 2, anytime. The 70 is the only outlier. Good for us. Similarly, blah, blah, blah. Race 2, there are no outliers. Yay, we did it. You don't have to calculate it by hand. You can just run those into a calculator and see what happens. Part B. Each dog ran in one race, but not both. The reason why they say that is because they want you to know that each race is independent of the next. Independent of that. That's important. If all the times are combined, does the new set of times have any outliers? Okay. Huh. Well, if I wanted to do that, I would just literally go to the bottom of L1 and just run this again. See what happens if they were combined. 61, 65, 67, 68, 69, 69, 70. Let's run a 1-var stat. 4 is the interquartile range. No. No, you'd have no outliers. If they were combined, there would be no outliers. They're 18 values, so the set has no outliers. Yeah. Just reran that calculation real quick. Explain the reason for the answer to B in relation to the answer to A. Ah, excellent. Excellent, excellent, excellent. It mainly has to do with that interquartile range, I believe. Oh, no, they're just trying to compare the two graphs. I was going to say something to the effect of the interquartile range on part A being much smaller than that of the interquartile range on part B. But they're just basically saying in the first race, 70 was on the high side. However, in the second race, had a number of values around 70, so 70 was no longer an outlier. It's almost like if you overlaid these two graphs on top of each other, it's almost like it would just give you one complete graph. Yeah, honestly, it's like, these clustered ones would fill in this gap right here. Yeah, that's pretty solid. Okay, I'm going to do one more problem. And then I'm going to call it a day here. Just want to make sure I get a good one. I'm almost at the end of my deck anyway, so. Come on, you. Oh, here we go. Perfect. Last question of the day. To determine how the American public feels about pulling troops out of Iraq, 2 surveys are conducted. One in Army magazine asking readers to respond concerning whether or not they support retreat from Iraq, and in one in the New York Times asking readers to respond concerning whether or not they support phased troop redeployment from Iraq. Give 2 examples of bias, which may have been introduced given the ways in which the samples were selected. Immediately, for the first sample, they're asking the readers to respond. In Army magazine. That is voluntary response bias, if I ever heard one. Also, in the first sample, that is a bit of undercoverage. Because who are the types of people who would be subscribed to Army magazine? People who are probably, very much pro-military. But at the same time, they're pro-military. Maybe they want to keep their military safe. I don't know. But it's definitely voluntary response. For number 2, for the second sample, I should say, phased troop redeployment from Iraq? What kind of wording is that? What kind of wording is that? I'm not even sure what they're even asking there. The back of the cards say. Both surveys lead to voluntary response bias. Are they asking them? Yeah, asking readers to respond. Yeah, so both are voluntary response, based on individuals who offered to participate, leading to bias, to which emphasis is typically given to people with strong opinions. Both surveys also lead to what they call selection bias, as readers of Army magazine and readers of the New York Times are not representative of the American public. That's a fair statement. I would mainly argue that the wording that they did on the wording that they did for the New York Times, phased troop redeployment from Iraq, as a person who was not very aware of what what that phrase means, I don't know how I would respond to that. The wording on that is very confusing. Explain part B. Explain how bias may have been introduced given the ways in which the surveys were worded. Oh, well, there we go. See, it helps if I actually did read this and suggest different ways to avoid that bias. By the way, for Army magazine, they said support retreat from Iraq because they use that phrasing, retreat from Iraq. That is definitely response bias. Because use the word retreat, and then people immediately have an emotional connection to that, or an emotional response, I should say, to that. The word retreat is loaded with emotion. There we go. Whereas the phrase phased troop deployment is too evasive, yet confusing. A more neutral wording would simply ask about support for pulling troops out of Iraq. Nice. Okay. Tomorrow is the AP statistics test. I am going to be live tomorrow before the AP test, probably until like probably 1:30. So I'll probably be live in the 12 o'clock hour. I'll post it in Google Classroom what I'm going to do, and I'll tweet about it as well. But I'd like to just offer, if you wanted to, another review session, but I don't want it to interfere with the beginning of the AP test, so I'm going to avoid 2 o'clock tomorrow, like the plague. Only because I don't want to mess. I do not want to mess with you guys logging on and making sure you're there for when the question's ready. So anyway, I will be in touch with you guys about that tomorrow. Have a good day.